All right, welcome to another explainer. Today, we're stepping right onto the factory floor to solve a massive industrial mystery, and we're going to do it using some foundational physics. We're going to uncover exactly why heavy machinery sometimes fails catastrophically right at startup, and how one simple, classic formula holds the key to diagnosing the whole shebang.
Okay, let's dive into this. On one hand, imagine a standard 10-kilogram block. On the other hand, a massive 1,000-kilogram industrial steel coil. Now ask yourself, to get both of these objects moving from a complete standstill, do they require the same amount of force? Well, the answer, of course, is a resounding no. But understanding exactly how much more force is required and how that impacts the motors trying to move them is literally the difference between a smooth-running factory and a catastrophic machinery failure. All right, Section 1, the real factory breakdown. Let's set the scene with a real-world emergency.
Picture this. You're the lead maintenance engineer at a large steel plant. You get an urgent call, which, let's be honest, never happens at a convenient time. The main motor on the rolling mill, that critical piece of equipment that flattens out giant slabs of metal, has suddenly tripped. The operator hit the start button, the motor drew a massive spike of electrical current, and boom, the entire system overloaded and shut down. Production is halted. And you know every minute the machine is down is costing the company thousands of dollars. So you have to figure out, why is this motor suddenly drawing so much current during startup? What is mechanically happening to cause this electrical failure?
Moving on to Section 2, decoding Newton's second law. Because the secret here isn't in an electrical manual. The foundation for sizing motors, designing cranes, building conveyor systems, all of it comes down to one singular, elegant equation. F equals ma, Newton's second law of motion. Force, which we measure in newtons, equals mass in kilograms multiplied by acceleration in meters per second squared. This formula tells us exactly how much mechanical effort is required to change an object's speed. Let's break down a quick, simple example. If you have a mass of 10 kilograms and you want to accelerate it at 5 meters per second squared, you just multiply them. 10 times 5 equals 50 newtons of force. Simple as that. So the crucial point is understanding exactly what a newton represents in the real world. 1 newton is the exact amount of force required to take a 1 kilogram mass and accelerate it by 1 meter per second every second. It's the standard go-to unit of push or pull in mechanical engineering. What Newton was really telling us through this formula is all about relationships. If you apply more force to an object, you get more acceleration, right? But if you have a really heavy object, so more mass, that exact same amount of force is going to result in far less acceleration. This relationship between force, mass, and acceleration, it's basically the invisible rulebook governing every single moving piece of machinery in a factory.
Section 3, real plant application examples. Let's take a walk through the plant and test this rulebook out.
Let's look at this conveyor motor scenario. And this brilliantly illustrates the real-world impact of acceleration on equipment sizing. We've got a 200-kilogram steel plate sitting on a conveyor. If we want it to start moving gradually, say an acceleration of 0.5 meters per second squared, we do the math. 200 times 0.5. The motor only needs to provide 100 newtons of force. Easy. But what happens if the production manager comes down and says, hey, we need this moving faster, let's ramp up the startup acceleration to 2 meters per second squared? Well, 200 times 2 equals 400 newtons. Just by quadrupling the acceleration, we have literally quadrupled the physical force required from that motor. And you know, the exact same principle applies to fluid power. Let's diagnose this hydraulic cylinder application step by step. Step 1, we identify our load. It's 500 kilograms. Step 2, we identify our target acceleration, which is a very slow, highly controlled 0.2 meters per second squared. Step 3, we calculate the required force. 500 multiplied by 0.2 gives us 100 newtons. If this hydraulic cylinder cannot produce 100 newtons of force, that 500 kilogram load just isn't going to accelerate at the speed we want.
Okay, Section 4, mass versus weight. Avoid mistakes. Let's talk about a major conceptual pothole here.
You must never, ever confuse mass and weight when doing these calculations. Mass is measured in kilograms. It is the sheer amount of matter in an object, and that doesn't change whether you're on Earth or floating around on the moon. Weight, however, is a force. It's measured in newtons. Weight is simply your mass multiplied by gravity. When we use F equals ma to calculate horizontal movement, we use mass in kilograms, not weight. If you plug the weight of an object into the m variable, your calculation is going to be drastically wrong, and frankly, you might just blow out a motor.
All right, I want to test your troubleshooting skills right now. Act as the engineer for a second here. What force is required to give a 20-kilogram block an acceleration of 3 meters per second squared? Just do the math in your head.
Got it? Bam, 60 newtons. If you took the 20 kilograms of mass and multiplied it by the 3 meters per second squared of acceleration, you absolutely nailed it. That's F equals ma in action.
Section 5, Solving the Motor Mystery. Let's head back to that broken rolling mill from earlier.
We can actually frame the solution to our breakdown as a classic mechanical engineering interview question. Why does a motor draw high current during startup? Well, our maintenance engineer stared at the tripped rolling mill and realized something. The operator had recently changed the machine's drive settings to start up faster. The required startup acceleration had been aggressively, artificially increased.
And so here is the exact domino effect our engineer discovered. By programming a high starting acceleration, Newton's second law dictated that a massive amount of physical force was suddenly required to move that heavy steel. To generate that massive force, the motor had to output a drastically increased amount of torque, and to generate that torque, the motor had to gulp down a huge amount of electrical current. That sudden, massive current draw is exactly what tripped the system and overloaded the gearbox. So the engineers simply went into the software, lowered the starting acceleration, which naturally lowered the required force, which lowered the current draw, and the rolling mill started up flawlessly. Mystery solved, all thanks to F equals ma.
If you're going to take away one simple field-ready memory trick from this explainer today, let it be this quote right here. More mass equals more force. More acceleration equals more force. Whether you're sizing a motor, diagnosing a trip breaker, or designing a conveyor belt, remembering this golden rule is going to keep you and your machinery operating smoothly.
But what happens when that massive force we've been calculating is applied to a tiny, concentrated area? Well, things break, snap, fail. The physics that make our factories run are the exact same physics that can tear them apart. In our next explainer, we're going to dive into the fascinating world of mechanical stress, exploring the formula sigma equals force over area. We'll be looking at some incredible real-world examples of thick steel shafts shearing right in half and heavy-duty bolts breaking under immense pressure. It's a real game changer, and you definitely won't want to miss it. Until then, keep analyzing, keep questioning, and I'll see you next time.